In this experiment, we're going to explore the pH of acids and bases. So we need to start off by defining what an acid and a base are. An acid is going to be a substance that donates hydrogen ions when it is in a solution, whereas a base is going to accept those hydrogen ions in solution. So suppose we take hydrochloric acid and we put it into water. What's going to happen is that this compound is going to dissociate into the ions that it came from. So it's going to generate a hydrogen ion and a chloride anion. And if we were to take sodium hydroxide and did the same thing, we dissolved it in water, it would dissociate into the ions that it came from, meaning it would generate a sodium ion and, that should be hydroxide, and a hydroxide anion. Now, if you were to mix these two substances together in the same flask, and I'm just going to indicate that they are aqueous because we are dissolving them in water, you can effectively treat an acid-base reaction like a double replacement reaction. So what we're going to do is take apart each substance into the ions that it came from. And then we're going to take a cation and give it a different anion. So here sodium was bonded to hydroxide, so we're just going to give it chloride instead. And that is going to leave the hydrogen ion with the hydroxide anion. When we do that, we are generating sodium chloride, which of course is dissolved in water, so it will be aqueous. And then when hydrogen and hydroxide combine, you're going to generate water. These charges cancel out, and water will be one of the byproducts. So this is the format of the acid-base reaction. You will always generate a salt, and you're always going to generate a water molecule. And this type of reaction is what we call neutralization, where an acid and a base neutralize each other to produce a salt and water. Now, the identity of the salt will really depend on which acid you start with and which base you start with. So it will not always be sodium chloride, but it can be any ionic compound depending on the identity of the acids and bases that you're using. So when an acid generates hydrogen ions in solution, we need to know how many hydrogen ions it is generating. What is the concentration? And the way that we measure that is using a concentration that we call molarity, which is abbreviated as a capital M. So if you see capital M, that is a type of concentration. We call it molarity, or we would say that this solution is some amount molar. So for example, let's say that your concentration is 3.00 m, we would say that's a 3 molar solution. Molarity is defined as moles of solute divided by liters of solution. So just to recap, a solute is what you are dissolving. In the solution. So the solution is going to contain the liquid that you're dissolving it in, typically water. So in all of these reactions, the solvent will be water. And the solute is what you are dissolving in that water. So let's say that we're making a 3 molar acid solution. We would be dissolving hydrochloric acid in that water. So hydrochloric acid would be the solute. And a 3 molar solution would indicate that we have 3 moles of hydrochloric acid dissolved in 1 liter of solution. So that is the definition of molarity. Effectively, what this means is that the higher the concentration of your solution, the more hydrogen ions we are generating. So let's say we take a 3 molar hydrochloric acid solution, and we said the hydrochloric acid is going to dissociate into the ions that it came from. If you had 3 moles of this hydrochloric acid in solution, that means you would be generating 3 moles of hydrogen ions when that dissociates. And of course, here I'm just writing 3 of them. In order for that to be moles of hydrogen ions, these would need to be multiplied by 6.022 times 10 to the 23, because that's what molarity means. If you were to have instead, let's say, a 5 molar, that means that you would have 5 moles of hydrogen ions that would be present in solution. So the higher concentration, the more hydrogen ions you have, and the more acidic that solution will be. If we examine the concentrations of hydrogen ions in acidic solutions, you would find that a lot of the time they're actually pretty small. So for example, lemon juice, this bracket notation here means concentration in moles over liters, which of course is molarity. So whenever you see a number included in these little brackets, it's saying that is the concentration. So if in lemon juice, if we were to take the concentration of hydrogen ions, it would be 1 times 10 to the negative 2 molar, which really means that you have 1 times 10 to the negative 2 moles of hydrogen ions per liter of solution. Or you could plug that in and get a decimal, and you would find that that's 0.01 moles of hydrogen ions per liter of solution. That is a pretty small number, and they can get even smaller than that. So having to deal with scientific notation and all of these exponents can be a little frustrating. So the way that we handle that is by using a different value that we call pH. So pH is really a measurement of how acidic or basic something is. And pH is going to turn this into a much more user-friendly format, where the numbers will be a lot smaller and easier to handle. So for example, if your pH is equal to 7, then the solution is neutral. And if the solution is neutral, it means you have the same amount of acid and the same amount of base in solution. And the hydrogen ion concentration that would correspond to that value would be 1 times 10 to the negative 7 molar. If the pH is greater than 7, then the solution is basic. And if you have a basic solution, it means you have more base in solution than acid. So in that case, the hydrogen ion concentration would be less than 1 times 10 to the negative 7 molar, because it's saying you have less hydrogen ions than you would in a neutral solution. If the pH is less than 7, then the solution is acidic. And in that case, you have lots of hydrogen ions in solution that are making this very acidic. And in that case, the concentration of hydrogen ions would be greater than 1 times 10 to the negative 7 molar. So converting these types of concentrations into pH can make things a lot easier, because then you're just looking at, is this number 7? Is it less than 7 or more than 7? So the scale will be from 0 to 14. The closer you get to 14, the more basic the solution will be. The closer you get to 0, the more acidic the solution will be. And there are a couple of equations that will enable you to convert between pH and hydrogen ion concentration. So suppose that you know the hydrogen ion concentration of a solution, you know exactly how many of those ions are floating around in there, and you want to know the pH. What you would do is use the following equation, that pH is equal to the negative log of the hydrogen ion concentration. So these brackets right here, this is telling you hydrogen ion concentration in moles over liters. So let's say we wanted to know the pH of that lemon juice that we had up here. We know the concentration. We could just plug that value in. So we would take a negative log of 1 times 10 to the negative 2. Alternatively, we found that 1 times 10 to the negative 2 really means 0.01. So you could enter either of these values. You could plug in negative log of 0.01 into your calculator, and that would give you a pH value. And if you were to do that, you would find that the pH is 2. If you compare that to our scale here, notice that this pH is less than 7, so this solution is acidic. And that makes sense for just based on what we know about lemon juice. We know that it's acidic. Alternatively, let's say that you knew the pH of a solution, but you didn't know the hydrogen ion concentration. So you know the pH, you want to calculate the hydrogen ion concentration. The equation that you would use to do that is that the hydrogen ion concentration is equal to 10 raised to the negative pH. So that will take you in the other direction if you know the pH value. So suppose that we know that the pH of the solution is 5. If we were to compare that on the scale, notice that that's greater than 7, so that would be a basic solution. And we want to know, well, how many hydrogen ions are there? We would raise 10 to the power of negative 8.35. We'll plug that into our calculator. And you will get, lots of zeros here. That would be 4.0 times 10 to the negative 9 molar. So very, very small concentration of hydrogen ions.